Okay, so next we have Vlad Matei from the University of Tel Aviv, and he's going to be speaking with us about counting pairs of projective plane curves with a prescribed number of FQ intersection points.
So thank you everybody for inviting me to give a talk. I hope everybody is doing well. You know, it's crazy times, but everybody's doing well. So I want to tell you a little bit about, this project that, a part of it is finished and a part of it is still ongoing. So, let me do some basic kitchen stuff, like tell you a little bit about the setup before we get into things. Okay, so for people who are not used to these, like, Pn is going to denote the n-dimensional projective space. That means the space of points, under this equivalence relation. Okay. For me, be careful about the definition. So some people like to decorate this, but for me, just a plane curve will just basically be the vanishing locus of a degree D homogeneous polynomial. And maybe here I should have been a little bit careful because I want to go over the algebraic closure. So that's a small kind of thing to note. And CD, this thing here is going to denote the set of all degree D curves. And again, note that I'm not imposing any conditions on the polynomial, so it's just everything. And the kernality is very easy to write down. In this case, it's an easy counting argument that this is the kernality of this set. Okay, good. Okay, and the Frobenius, let me not forget, this is going to be important. Frobenius is going to be this map that takes z to the power z to the cube. Okay, good. And the question that I want to answer and tell you a little bit about it is, okay, so imagine you take all these curves with one of degree D and one of degree E, then you want to count them such that they have a fixed number of intersection points. And obviously, the interesting range for us is going to be 0 to D. This is because of Bézout's theorem. So technically speaking, if these were irreducible curves, then you would expect some number between 0 and DE. Their D with multiplicity over the algebraic closure, but here we're interested in the actual things that are in the finite field. Okay, so they're defined over our finite field where also the curves live. Okay, so that's the main question. Okay, so I want to tell you a little bit about some general answers that we have to this question before I get into anything else. So let me make first this remark, that if you take the intersection points of these two curves, then what you get is an interesting set, but it also comes endowed with the action of the Frobenius. Namely, it's the same idea from Galois theory that you see all over the place, that if you have like roots of a polynomial, the Galois group acts on these roots. It's kind of the same principle that in this case, you get the Frobenius action on this set. And now, if you assume that the intersection is transverse, you don't get any multiplicities, which is the generic case, and everything is distinct, you get some permutation on, DE and SDE, because again, here secretly we're working over the algebraic closure. So to get, the permutation here in SDE, you need to work over, the algebraic closure to see this permutation. And now if you were like gambling, you would say, okay, what's the other obstruction that might, happen? There's nothing that should happen, right? So if you want to get K points over the projective space over FQ, then you could say, okay, Frobenius has to fix K points. So maybe if everything is like a random permutation, that your answer might be like, okay, how many permutations have K fixed points inside this thing here? So that's one guess for what the answer should be. And actually this guess turns out to be right, except you need some decorations for it, okay? So this group is actually called the monogamy group. So the main result that Antin proved is that indeed this monogamy is SDE, the symmetric group on DE objects. It's more general than that. I'm not gonna say all about it, but in the particular case we're interested in, this is going to be the monogamy group. And as a consequence, if you apply Chebotarev, you get this count here. So you get that your guess was right. So this justifies that your guess that you would get permutations that have, k fixed points is right in this case. And you get some error term, which, be careful, depends both on D and E, and it's some small savings. So if you want an answer, this is good enough in the regime that Q goes to infinity. Okay, so because you can't control what happens with this things with D and E there. Okay, so that's one possible answer. Here's another fun answer you can do by yourself. So this is another very easy exercise, that when you have very large degree curves, imagine what happens if you take D very large. So in this case, it's enough to take them bigger than Q squared plus Q. Then every point in the projective space over FQ is going to behave like an independent thing. So passing through a point and another one is independent, of each other. So that means you can phrase, this thing probabilistically, and you get this other kind of interesting probabilistic result that tells you that having k intersection points is equal to the sum of random variables. And again, be careful. There's no declarations about being smooth or not, because if we're talking about smooth intersections, then this is a subject of a paper of Kedlai and Booker. Okay, so they have this idea where you have, smooth intersections, but here, just do the naive thing for every pair of curves and you get this. And it's interesting because you can kind of unify these two perspectives and say that you expect kind of one intersection point. So if you play around with what happens here and you play around with what happens here with the expected value, you would roughly see one intersection point. So kind of, there's a way to unify these two perspectives into one. Okay, but enough about, the previous results. Let me tell you a little bit about what I want to do. So how about exact counts? So in this case, you want to keep Q fixed and you want to take D any arbitrary. So, you want to get some concrete expression about what this is. And let me say that in general, if you ask this question, it's very unreasonable of me to ask this, because this is the same difficulty of asking you how many curves over, FQ, let's say of degree D, sorry, over the projective space, have like Q plus 1 points. We don't know a good answer to this unless you make Q large or make the degree very large. So, asking this formula in general, it's very unreasonable to expect a good answer to it. But at least in work with Nathan Kaplan, we can give some answers to this question. So initially we did this using some very different techniques, as you'll see for these cases. Like these are very low degree cases. But actually, it turns out that we can soup it up to make it a low degree case and arbitrary degree. So conic. So basically, this is conic and conic, conic and cubic, and cubic and cubic, and then you can do conic and cubic and arbitrary degree. Okay, and I would say that this is the border case. We can't go any further than that, and you kind of understand, why this is the border case as we go along. Okay, so let me jump in and give some formulas, since I promised I'm going to give some explicit counts. Namely, we show in one of the papers that's already in ArcSiv that the number of pairs of a conic and a cubic that intersects in exactly 2 FQ points is this one. So the form of this is a bit weird. This is due to the fact that we're using Sage to compute this out. So I'll explain a little bit where the computer algebra part comes into play. But if you actually multiply everything together, you get exactly the main term, which is 3/16, which is exactly the thing in S6. So this is the proportion of permutations with exactly 2 fixed points in S6, this term here. So that's the main term. And then, you get this polynomial count. So this is, polynomial, which is very nice. Okay, let's do something harder. Let's do cubic and cubic with the same kind of things we do in the paper and the algebra system. We can prove this count, which looks a little more horrible to compute by hand if you try to do this. Okay, so we get this number. Okay, and finally, this is I want to say a little bit towards the end about this more interesting count. Namely, if you have a cubic and a degree D intersecting in k FQ points, then you're going to get, again, the main term that you expect, because there are 10 here I don't care about scaling. So that's why the 10 shows up, because that's how many cubics we have. And then you get some expansion like this. And these terms here are going to come from the action of the Hecke operating acting on cusp forms of appropriate weight. Okay, so basically it has to do with modular forms in the end. So that's kind of the takeaway from this. And what I want to point out is that now these are going to be non-polynomial answers. So because you get these Hecke operator traces, then you get basically a non-polynomial answer. So you already see the complication of this problem even showing up when you do degree 3 and arbitrary degree. You don't get any more this polynomial behavior. Okay, and now I want to say a little bit about the methods that go into.
Sorry, I'm a bit confused.
But are there any questions about things?
Sorry, can you hear me, Vlad?
Yeah.
I'm going to ask a few. I'm a bit confused. You do have a polynomial in Q, but you're saying A and B are not polynomials. And
so because A and B, these coefficients come from the traces of the Hecke operator. Mm-hmm. These are technically they have some square root of Q involved. So I'm kind of lying about the form of the answer because we haven't worked this out, but technically what we should get at the end is that there should be something coming from traces of the Hecke operators. So the way I've written it might be a little lie because this is not going to be quite exact like this, but except for the first term, this one, the rest of the terms after that should come from these traces of the Hecke operator. Does it make more sense?
So the way you've arranged it, this is like the highest order term or something. And did you say what f of k 3D was? That's some.
Yeah, so this was on the previous slide. This is the number of permutations with the k fixed points.
Oh, okay.
In SD. Okay, so the main term agrees with what you know from before.
And so, okay, so in general, okay, sorry, just summarize. In general, you have three parameters. You have the number of FQ intersection points and you have the 2 degrees. And you're saying
exactly.
we should not expect a polynomial in Q for general DK, but is there anything we can say in general about?
Yeah, so basically what I want to say is that I think the cases that I wrote before, the 2-2, the 2-3 and 3-3 and in general conic and a degree D, you get polynomial answers, and actually we get also 2 and D. I didn't write it, but it's a polynomial answer. But after that, you expect non-polynomial answers. I don't have a, I can't justify this in any mathematical way, but intuitively this is what reasonably should happen. You land into like generally you have a general curve, kind of, or a general parametrizing variety, and there should something there's nothing you can say about the point count, except that, they might lie somewhere, but you can't say too much about the geometry of that variety, that parameterizes the intersection points.
Okay, awesome, thanks.
Okay, good. So let me say a little bit about the methods that are involved. Okay, so for the first 2 theorems, we're gonna use a little bit of ideas from coding theory, algebraic geometry, and number theory. So for the first 2, we're gonna use this one, coding theory. So let me say a little bit about the setup. So what's a code is just going to be a subset of this vector space, and it's a linear code if it's a linear subspace. And now you can introduce what is called the Hamming weight of a vector. Is just the number of its non-zero coordinates. Okay, so that's just going to be that. And then you can put everything together into a generating function. Okay, so you can put everything together into this kind of generating function for any code you want. Okay, and what does this have to do with curves? But let me say a little bit about that. Well, you just take all the points in your projective space and you choose some affine representatives for them, and just take this map from this space of polynomials, to the fq to the n, where n is the appropriate dimension, and you just evaluate at every point. So you take your polynomial, just evaluate it at every point. You're going to get this vector in this huge space, and that's going to give you some code by this procedure. Okay, so you get some code and you have some dimension for it, And it's a very special type of code. So people in coding theory call these projective read Molar codes. And what this has to do with our problem is that, for example, the weight enumerator is going to give you, if you're doing curves of degree D in P2, so this is degree D in P2, so this is degree D in P2. This coefficient is going to keep track, for example, how many curves have exactly I points. Okay, so it's some generative function that keeps track of that. Okay, and now there's something dual that you can do, and I'll explain why you need that. So you can introduce this orthogonality relation, and you can do the orthogonal of a code, which is called the dual code. So sorry for skipping this, but yeah, I didn't time myself too well. But what I want to say is that, okay, the code itself keeps track of some interesting information about, how many points do you have. The dual code keeps track of something even more interesting. Sorry, so I should highlight this. Namely, dependent conditions on curves, okay? So you want to see, how many curves do you expect passing through a set of D points? Well, you're going to be unlucky sometimes. So for example, if you have a lot of collinear points, then your line is already contained if you have too many. Like if you have a degree D curve, if you have the curve contains D plus 1 already of those things, then it contains the whole line. So adding an extra point doesn't give you any information. Okay, so, and there's a relation that you can go back and forth between these two counts. And what do we do? Well, for us in the theorems 1 and 2, we're going to do something that parameterizes the intersection points. So there's a way to do a general Hamming weight enumerator for the intersections. Namely, this is going to come from the code that it's a matrix. So it's going to have, this matrix is going to have rows C1 and C2. And you can define the weight in a similar way, which are non-zero columns for this. And you can do that. And then we're left with, in our count, Bezout allows you to do the high weight coefficients because you share common components. And for the low weight coefficients, we're going to do some linear algebra. So we're going to go to the dual, and we have to understand basically small sets of points that impose dependent conditions. And then, the computer helps us solve this linear system that comes out. So let me say a little bit about, dependent conditions. Okay, so when does the codimension is not what you expect? Like you would have, more curves than you expect passing to the set of points. Well, in general, this is a hard question, but at least there are some partial answers to this question about dependent conditions. Okay. Namely, if you have a small set of points, then you can say something, they are on a line, as I said, or maybe they're on a conic. Too many are on a conic. Okay. So yeah, I don't want to have time to get too much into the other stuff, like the more interesting stuff about what we can say. So, but let me say a little bit just about how do you work with theorem 3. And then I'll stop. I don't want to go too much over time because that's a bad habit. But for theorem 3, I want to say that the problem gets a little more interesting because it turns out that if you want to count curves that pass through these points, we are left with this interesting problem that when you have this many points on a smooth cubic, they are going to come from the intersection with a plane degree D curve if and only if their sum of the points is going to be the 0 element in the group law. Okay, and you want to count basically this collection of points to do your count for the number of pairs of curves. And this count turns out to be very interesting because that's where the Hecke thing comes into play. So there's a combinatorial way to set up this problem. And at the end of the tunnel, you end up with these kind of sums that look like this. And that's where the Hecke operators come into play, and actually work of Petrov and Kaplan is going to heavily used to actually control these sums. Okay, so let me stop here because I don't want to go too much over time, but if you have more questions, I'm more happy to explain. And I'm also happy to put these slides if you want on the website for the pajamas. Okay, and then there's more info there, but sorry for going a little bit too fast. I didn't time myself too well.
So let's thank the speaker. And are there any questions?
I have a quick one.
Yeah.
Which is, can you say very quickly where the modular forms come in?
Yeah.
Oh, wait, no, you say that at the end. Never mind.
Yeah. Yeah.
Great.
Other questions?
So the reason why elliptic curves come up is because you are dealing with cubics, right?
Yeah, so because of cubics, we have this lock that this happens to be true. And what I haven't said, I skipped this slide, is that you can sub up this condition about independent conditions. So there's this result of Hakopian and Malinian that tells you that, okay, if you're not on a conic, not too much is on a conic and so on, you're only gonna have troubles when you run into these kind of things, like at the edge of the boundary of independent conditions. Okay.
So can you say what your conjecture is if it is a plane, if it is a degree 2 curve and a degree D curve? So what is in place of the modular form or elliptic curve?
Oh yeah, so there is going to be just a polynomial count. What I haven't said is that there you can just easily do it, and it's just going to be a polynomial count. You can easily just use this one, for example, to write down carefully what you get. Because this 2D, so you have at most 2D intersection points. So the only trouble you run into is like having points on a line. Like that's the only obstruction, and then you just have to carefully write the codimensions and just do the combinatorics. There's really nothing too complicated about that. Does that answer your question?
So by your count with degree 3 and 3, you have written that down, right? And that seems to be polynomial count, and say that was a coincidence. So
no, so you don't get any more. So again, the only polynomial counts you get is for degree 2 and degree 3 arbitrary, and degree 3 and 3.
Oh,
and I assume
see.
After that, it stops to be polynomial.
So is there some like high-level reason why the degree 3 and 3 is sort of a coincidence where you still have polynomial count?
So it's because, one philosophical reason is that there it actually happens that these traces of the modular forms actually turn out to give you polynomial counts, so they kind of vanish. This is in a paper of Old Purple of Birch, and also Nathan has written a paper about these kind of things. Like there, when you sum up these traces to the power up to the power 9, it actually turns out to be, polynomial, to give you polynomials. Like the sums that I've written here, forget about, so that's one philosophical reason. Other is that, okay, if you forget about this, for 0 less than k less than 9, you get polynomial counts for these things in terms of Q.
Thank you.
Yeah.
Are there any more questions? Okay, well then let's thank our speaker again. And we have about 5 minutes until the next talk starts at 10 after.